So why does helium make the pitch of your voice increase? The answer to that is in what we call the root mean square velocity of different gas molecules. A molecule that has a higher velocity will have a higher pitch. So we can calculate what we call the root mean square velocity of different gases. First, let's talk about what root mean square is. Root mean square is a statistical trick where you can calculate not the average, but something akin to the average. The problem with calculating an average velocity is you've got some gas molecules and they're traveling in different directions. If you were to calculate the sum of all of these, add them all up, then the average velocity would equal 0 because they're all traveling different directions and their velocities would cancel each other out. But if we labeled each one and instead of just adding them together, we took the root mean square, which basically means squaring each one of these. We'll add them all together and divide by however many molecules there are. And then we take the square root of that. That is a root mean square. And basically that just cancels out the directional component of the velocity and gives us an average velocity without ones traveling in opposite directions adding to 0. We give this the symbol. Velocity is that V, and RMS stands for root mean square. And you can actually derive an equation. You can do this using the postulate that the kinetic energy is proportional to the temperature. You can actually write that out as an equation. The kinetic energy then proportional to the temperature, but equal to 3 times the ideal gas constant times the temperature divided by 2 and Avogadro's number. Also, kinetic energy is equal to 1/2 m velocity squared. So kinetic energy is dependent on the mass as well as the square of the velocity. So then we can just get rid of the middleman and set these two equal to each other and rearrange for velocity. We'll give you 3RT over m times n square rooted is equal to the velocity. And this m times n, this is the mass times Avogadro's number, which is the same as the molar mass. So the most common way that you'll see this equation written is the root mean square velocity is equal to the square root of 3RT over the molar mass. Okay, so you can use that equation to calculate the average velocity of any particle as long as we know what temperature it is at, because the higher the temperature, the faster that particle will be moving, and which substance it is. The heavier the substance is, the greater its molar mass, the slower it will move to contain the same amount of kinetic energy. So when we're talking about root mean square velocity, we know we're going to use this equation that we just derived. Now this, let me warn you, is a little bit trickier than it looks at first glance because you want to make sure you write out your units so you can see what is canceling. I'm going to show you how we might immediately plug it in and show you why that doesn't work. And then I'm going to show you the correct way to do it. Okay, so we might say, okay, so 3 times R, 0.08206 atmosphere liters per mole Kelvin, times the temperature, 298 Kelvin. So to get from Celsius to Kelvin, remember we add 273. And then I'm going to divide it by the molar mass of helium. So that's going to be 4.00 grams per mole. Now, it's really important to write out these units because now we want to look at it and see what cancels. I see that Kelvin cancels here and moles cancel here, and that leaves us with units of atmosphere liters per gram. That means once we take the square root, we have units of atmosphere liters per gram to the 1/2 power. Now, I don't know about you, but those aren't units of velocity that I've ever heard of. So we know there's something wrong with our units. So let me show you over here on the right side the correct way to look at your units. It's really important to write them out so that you can recognize they didn't cancel, you made a mistake. You can express R as 0.08206 atmosphere liters per mole Kelvin, but there are other units that you can express R in. Just like you can express the length of your notebook as 11 inches, you could also express it as like 30 centimeters. It's the same distance, but you're expressing it in different units. So we can do the same thing with R. So instead of expressing it in atmosphere liters per mole Kelvin, we can express it in joules per mole Kelvin. And then the temperature, we're still going to keep that in Kelvin because we need an absolute scale. And then our molar mass. This is still not quite right, but I want to show you that we're getting closer. Now if we look at what cancels, we see the moles and the Kelvin cancels, and we're left with square root of joules per gram. Now, the key to solving this is knowing what a joule is. A joule is a unit of energy, a form of energy that you might be familiar with. Work. If you've taken physics, you might remember that work is equal to force times distance. The unit for force is newtons, and force is mass times acceleration. Okay, we're almost there, I promise. Okay, so mass, the SI unit of mass is kilograms. Acceleration means distance over seconds squared. That's our SI unit of force. Newtons is kilogram meters per second squared. Now we have that here times distance again. So the unit joules means the same thing as kilogram meter squared per second squared. So whenever you see joules, you could write joules, or you could write this like broke down version of what that means. So let me change this joules here to the unit kilogram meter squared per second squared. Now remember that was joules per mole Kelvin, so all of that still goes in there. Okay, so our moles and our Kelvins still cancel. And now, interestingly, we have this unit meter squared per second squared in here. When you take the square root of that, that's going to be meters per second, which is a very nice unit of velocity or speed. The only thing that we have left to look at is here I have kilograms and here I have grams. But it's easy enough to convert between grams and kilograms. You just divide the grams by 1,000 and then they nicely cancel. All right, so I know that the first time you see this can be overwhelming. So the takeaway, the practical thing, is when you are calculating root mean square velocity, you need to use the R, that is 8.314 joules per mole Kelvin, because that is the same thing as saying kilogram meters squared per second squared mole Kelvin. I know that's a mouthful. And you need to put your molar mass into kilograms per mole. So you have to divide your molar mass by 1,000 for all of your units to cancel. Okay, so if you do that with helium, then you see that the root mean square velocity of helium is 1,360 meters per second. To give you a frame of reference, the root mean square velocity of air is roughly 500 meters per second or so. And so we would expect helium to have a faster root mean square velocity because it weighs less. And that's why when you inhale helium, it makes your voice sound higher because it's moving more quickly through your vocal cords. All right, it's time to pause the video and try another example yourself. So we're going to do the same question, but I want you to see if you can calculate the root mean square velocity of sulfur hexafluoride at room temperature, which is 25 degrees Celsius. Okay, the root mean square velocity of sulfur hexafluoride at 25 degrees. Remember, the equation is 3RT over the molar mass. We are going to use 8.314 joules per mole Kelvin for our R, but I'm going to just go ahead and directly change that joules to its breakdown, which is kilogram meters squared per second squared. And I'm including this mole Kelvin here, okay? And then the temperature in Kelvin. And the molar mass of sulfur hexafluoride is 146.06 grams per mole. But to cancel out the kilograms here, we need to put this into kilograms too, which means we'll divide by 1,000. So we have 0.14606 kilograms per mole. So the molar mass is 0.14606 kilograms per mole. Now let's make sure all of our units cancel. So the kilograms cancel, moles cancel, kelvins cancel, which leaves us with meters squared per second squared. If we put this into our calculator, we get square root of 50,888 meters squared per second squared. Then we'll take that square root and we get 225.6 meters per second. Notice how I square rooted the number and I also square rooted the units. Meters per second is a nice unit of velocity, so we know we did our calculation correctly. Also, we should ask, does this make sense? Sulfur hexafluoride is heavier than air, so that means that it moves slower. We said air moves about 500 meters per second, so that means our answer makes sense. So then the last question is significant figures. We'll go back here to our measured value. 25 plus 273 has to end in the ones place, which leaves us 3 from the temperature. We have 4 from here. This 3 is an integral part of the equation, so it's actually an exact number. And the 5 from our molar mass means that our answer needs to be rounded to 3 significant figures, which means the root mean square velocity of sulfur hexafluoride at 25 degrees Celsius is 226 meters per second.